Hello, and today we are moving to chapter 2, Plastic Hinge. First of all, let me make a review on moment curvature relationship. In the previous week, we already consider a beam having a rectangular section under bending moment. You are very familiar with elastic phase. In elastic phase, we have sigma equal to E epsilon and moment equal to AI pi. For elastic limit, we have sigma equal to sigma y and my equal to EI pi y. So this is moment corresponding to elastic limit. And the elastic plastic phase. What is M? So in elastic plastic phase, the moment is a function of My or MP. Moment is a function of My or MP, and a function of here of Y upper line. So we already have equation M equal to this is function of My or is function of MP. So normally we use this equation. Okay, so remember M is function of MP multiplied by this one Y applied over D square. And fully plastic MP equal to P D square sigma Y. It is plastic, fully plastic. On the section sigma equal to sigma Y. So we have the relationship between moment and curvature, and this is moment curvature curve depending on the different phase. So with different phase, we have different relationship between moment and curvature. Now is I section. Consider an I section or W section. We have I section with B and 2D, and the thickness of the web is TW, and thickness of the flange is TF. This is elastic state. In elastic state, sigma m smaller than sigma y, and we can divide the section into 3 parts, 1 and 2 and 3, and doing the equilibrium equation, then we can calculate moment of the elastic state equal to equation 2 to 1 in the textbook. So please check in the textbook for moment. For elastic limit, in elastic limit, and we have a sigma equal to sigma y, and again for dividing the section into 4 parts, 1 and 2 and 3 and 4, and doing the equilibrium, then we can calculate MR equal to equation 2 to 5 in the homework. Sorry, in the textbook. Okay. For the elastic plastic phase, we can divide a section into 3 parts, 1 and 2 and 3. One part corresponding to flange, and the second part corresponding to the section in the web with plastic, fully plastic, and the part 3 corresponding to the web, but in elastic. Okay, so finally we can calculate mi equal to this equation in textbook. Please check. And fully plastic, then MP can be calculated by this equation 2 to 10 in the textbook. Okay, so for I section, 4 different equations can be used to determine the moment corresponding to 4 different states of I section. And finally, we have a relationship between moment and curvature like this. And this is for rectangular, and this is for I section. And I section with resonance strength. This is the dotted line present the effect of resonance stress, resonance stress. Now, chapter 2, plastic hinge. First, we are going to determine the plastic hinge length. Okay, so now let's consider a very simple beam. It is simple beam with rectangular section. The section has B and 2D, and the load, it is a concentrated load in the middle of the beam. The beam has length of L. Then we are going to calculate the length of the plastic hinge. So here, this one is plastic zone. Okay, plastic zone. And we are going to determine this zone. Then, as you already know, in plastic analysis, we have for the simple beam, we have plastic load, limit load, QP equal to 4 MP over L. And the reaction is QP over 2. And this is moment curvature, moment diagram. The maximum moment is in the middle, MP. And maybe here is MY. MY is here. MY means the elastic limit. Okay, elastic limit. Let's go here. Now we are going to determine the delta L. How to determine delta L? You can see here delta L equal to the length of the beam minus 2A. A and A. Very simple, right? So to determine delta L, we have to determine A. Can you calculate A? Very simple, right? So A is a function of maybe My and the reaction. Is this right? So what is the relationship? We have QP over 2, that is reaction, multiplied by the lever M. It is lever M. Then we have equal to My. Okay, My. From this equation, it is very simple to determine A. So what we have? A equal to 2 My over QP. And of course, it's equal to 2 My over, this is QP. Okay, here is QP. Equal to this. And finally, we have A equal to L over 2F. What is F? F is shape factor. Shape factor, you should remember shape factor. F equal to MP over My. Okay, so this shape factor is it depends on the shape of the section. Then Now we have A is function of L and the section. Then finally we can calculate delta L, the length of the plastic hinge or plastic zone. Delta L equal to L minus 2A, or equal to L multiplied by 1 minus 1 over F. Okay, very simple. So now again, delta L, the length of the plastic hinge, is function of the length of the beam and the section, shape of the section. For I section, we have F equal to 1.12, so delta L equal to 0.1 L. For rectangular section, we have the shape factor is 1.5. Then delta L equal to 0.33 L. Okay, so we can determine the delta L, the length of the plastic hinge. Okay, now we are moving to next step. How to determine the boundary condition, the bound between the plastic zone and elastic zone. So in another word, how to determine the equation of this curve. Okay, how to determine the equation of this curve. That is what we are going to consider. Boundary between the elastic and plastic region. First of all, what is the moment of this point? What is moment of this point? So moment on this curve, but in a section. So this is section. This part is plastic, okay, and also because it is symmetric, so the upper and lower part is plastic, and the rest one, let's say, is one. This is plastic, and the region 2 is elastic. And how to determine MR at this point? Why apply? Do you remember? This is elastic plastic region. Elastic plastic phase. Okay, elastic plastic phase. So we already have the equation of M that M greater than My and smaller than MP. That is elastic plastic phase, and you already know how to calculate M. Here, elastic plastic phase. Do you remember? It is a function I just mentioned several minutes ago. M is function of My. M is function of M Y and apply, or is a function of MP and Y applied. Okay, I will remind you. It is in the previous week. M in elastic plastic region, M greater than My and smaller than MP for rectangular section, and we take integration of plastic and elastic, and finally we have this equation. M equal to the function of My or MP. So M equal to M is a function of MP, and y applied. Okay, so we can use this equation. In another case, you have to determine m as a function of mp and y applied. So now back to the problems. We have mr apply and y apply equal to the function of mp and this one y applied. For rectangular section, if we use I section, then you have to check what is mr y applied. And what else? Okay, so sorry. Now, what is m here? It is mx. Can you determine mx? Mx is m of this section. Okay, of this section. It is on the structure. M here is for section. M here is for structure on the moment diagram. So what is mx? Of course, mx. So we have this rectangular. Okay, rectangular. We have mp. We have x, and we have this length L over 2, and also we have this length L minus L over 2 minus x, something like that, and you can calculate x as a function of L. So it is rectangular, so it is very simple to calculate mx, right? So we have mx equal to this. It is a function of mp and L and x. Okay. So it is for structure and it is for section. And of course, mr should be equal to mx. mr y upper line should be equal to mx. Moment on the section should be equal to moment on the structure, moment diagram. So this one equal to this one. Then we can determine this one, y apply, is a function of x and mp, right? It is we have mp, we have x, and L is L. D is D. It is section, and it is length of the beam. And we calculate my as a function of mp and x. Y apply is a function of x. Here, y apply equal to d square root of 6x over L, or y apply equal to a function of x. Then this is equation of this curve. Okay, this curve, and also this curve. It is symmetric. Okay, so by using this equation, you can determine very exactly this curve. So now we can determine the length of the hinge and also the boundary between the elastic and plastic region. Full plastic moment. In this section, I'm going to talk about how to determine the full plastic moment of a section. Okay, of a section. If we have a section, then how to calculate MP? MP can be calculated by this procedure. First, you have to determine the P and A. P and A mean plastic neutral axis. Okay, plastic neutral axis. We have elastic neutral axis and plastic neutral axis. It is different. Plastic neutral axis is determined by divide the section into two equally part. Okay, equally part. So because of this, we have F1 and F2, and F1 should be equal to F2. Okay, so this is the condition, the first condition to determine the P and A plastic neutral axis. F1 equal to F2. So in this case, sigma y, here is sigma y, for example. Then here should be sigma y. Then it has F1 equal to F2. If in a compression and tension, the yielding stress is different, so it is not divided into two parts like this, but depend on the F1 equal to F2. So then after that we calculate F1 and F2 equally, and then we have to determine this, for example D. Then M now equal to F1 multiplied by D. It is MP. Okay, MP. And F1 here equal to A over 2 multiplied by sigma y. Right, very simple. And this is level M, or the distance between M1 and M2. For example, if we have a triangular section like this, and we can determine the P and A here, is divide the section into two equal parts. Okay, the first part and the second part, and the area of the part is A8 over 4, of course, and this is D. This level M between F1 and F2. F1 and F2 is opposite. Then very simple, we can calculate MP equal to A8 here over 4. This is section multiplied by the level M and multiplied by sigma y. Okay, sigma y. So again, in this case, sigma y in compression and in tension are the same. Okay, compression and tension are the same. Then we divide the section into two equal parts. If it is compression, sigma C, and it is tension, sigma T. If sigma C not equal to sigma T, then how to determine the P and A, and how to calculate MP? Think about that. Okay, think about that. It is key. F1 should be equal to F2, and by using this condition you can calculate P and A, and then you can after that you can determine the D, level M, F1 and F2 depending on the area of the upper section and lower section, and then you can calculate MP. Okay, so be careful. If sigma in the compression and tension is same, very simple, divide two equal parts. If not, be careful, consider F1 equal to F2.